Good evening. Yes, I'm audible, clear?
Yes, sir, you are audible. Good evening, sir.
Good evening. Yes, let me start.
Yes, sir.
Briefly introduce yourself.
Okay. Good evening, sir. My name is SubodhCheM, and I have done my schooling from St. Senior Secondary School, Rajasthan. And then I went for my graduation to the Central University of Rajasthan. And from after that, in year 2017, I have qualified the IIT-JEM exam. And in that exam, I got 264 rank. And after that, I got selected in the Indian Institute of Science. And from there, I did my post graduation. And after my post graduation, I have qualified CSI NET and GATE exams in the year 2021.
Yes, good. Yes, nice intro. Today mock topic is coordination chemistry. Yes.
Yes, sir.
Yes, let's start. Coordination chemistry briefly.
Okay, sir.
Basic to high on whiteboard.
Okay, sir.
Yes.
So when we talk about coordination chemistry, we usually talk about the coordination or chemistry. 2 points are there. So first one means coordination or chemistry. So it is a coordinate type of chemistry. So what do you mean by coordinate type of chemistry? So the definition tells that it is a branch of chemistry which deals with formation of coordinate compounds. So the coordination chemistry is a branch of chemistry which deals with the formation of coordinate compounds. So the important point in this is that the coordinate compounds. So what are the coordinate or coordination compounds? So coordination compounds these are the compounds which have coordinate bond. So in this, we are having coordinate bond. Those compounds are called as coordination compound. So coordinate bond is not a simple bond. It is a special type of bond. So coordinate bond it is a type of bond formed by donation of electron from one species to other species. So what we mean by this is, first thing, let's say for example a molecule is there NH3. It is having a lone pair of electron, and for example let's say a metal is there which is cobalt 3. So this metal is having a vacancy in the orbitals. It is having least number of electrons that it should have, hence it's acquiring positive charge. And ammonia has a lone pair of electrons for the donation which it can share or donate with the other molecules. So if ammonia donates its two molecule to the cobalt, we represent this bond by an arrow. This means that the two electrons have been donated from the ammonia to the cobalt, and the formation of this bond is called as coordinate bond. Now, in this topic, let's move to the next point. The next point is that we have studied about the coordinate bond, and we have also seen how it is formed. But what are the coordination complexes and how they are formed, or what are their features? So, let's take an example. For example, if a molecule we are having, like we are having a case of Mohr salt, then we write the Mohr salt as FeSO4 dot NH4 whole twice SO4 dot 10H2. Now, if we add water to it, then we can say that the ions of the Mohr salt will dissociate in the waters, and it will lead to the formation of Fe2 plus. Means the ions have been dissociated into the individual ions as their Mohr salt gets solubilized in the water. But let's take another example. This is K4FeCN6, potassium ferrocyanide. So if we dissolve this in the water, we will get these ions. So from this, we are seeing a difference in both the complexes, as this ion, this complex which is more salt, is retaining its identity in the water also. Like if we are dissolving this molecule in the water, the FeSO4 is getting dissociated into Fe2 plus and NH4 2 plus ions. But if we dissolve the complex like K4FeCN6, we are seeing that the FeCN6 part is not getting dissociated into individual. So what has affected this thing, or why this ion is not getting dissociated? It's all about the coordination chemistry, because this molecule is a coordination compound. Now, from this we can see that the coordination compounds are having property that the ions which are forming the coordination compound lose their individual identity as the ions. After the formation of compound, they have the properties of the complex only. They don't behave as individual ions. Now, the coordination compounds were first explained by the Edward Werner, and he is known as the father of coordination chemistry, and he gave us a theory which is called as Werner's theory of coordination compound. So, first point in the Werner's theory is that he told that each compound have two types of valencies. Each compound have two types of valence. What are these two types? These are primary valency and secondary valency. So what is mean by this postulate? Let's see. Let's write all the questions. Second thing he told that primary valencies are ionizable valencies. While secondary valency are non-ionizable. Then third point he told that primary valency are non-directional in nature. While secondary valencies are directional in nature. And fourth point, the secondary valencies determine shape or geometry of the cone. So these are the 4 points which Werner gave. Now let's understand all these 4 points. What is meant by these 4 points? So let's take an example again of K for efficiency. So the first point was that the complex have both primary and secondary valency. So what is meant by primary valency? So in this complex, we can see if we write it as 4K plus FeCN6 4 minus. So this 4K plus is getting dissociated. So the primary valency is the oxidation number that appears on the coordination sphere or this square bracket. So it has a primary valency of 4. And the secondary valencies are those valencies which are attached inside the square bracket. So it has a secondary valency equal to 6. Now, if we talk about second postulate, that was the primary valencies are ionizable in nature, while secondary valencies are non-ionizable. So this means that from above point we can see also that the primary valency is getting dissociated into the ions when we are hydrolyzing it, but the secondary valency is not getting dissociated into the. So this is meant by the ionization. The primary valency is ionizable, while the secondary valency is non-ionizable. Third point was that primary valencies are non-directional and secondary valencies are directional. So let's draw this complex. This is the structure of the complex. It is an octahedral structure. You are going to see later in the chapter how these structures are arriving. But let's assume that this is the structure. So the Cn minus, which are attached to the iron, they are obtaining certain directions and they are providing structure. So this is meant by the directional property. that the secondary valencies, whatever are attached to the coordination compound, they are directional in nature, while the K plus ions are somewhere outside the coordination sphere, attached just to neutralize the molecule. So this is meant by the non-directional. They are not providing any direction, whereas the Cn minus ions are providing directions. And fourth point was that the secondary valencies provide shape or geometry, as it can be seen in this point only, that they are providing certain kind of shapes and geometry to the coordination complex. So let's move to the next topic. So the next topic is, let's define the terms, because here we are having different terms. So we can define those terms. So first term which we need to define is ligand. So ligand is defined as any entity, whether it is ion, molecule, or atom, which can donate a pair of electrons. Second thing, coordination sphere. So coordination sphere is defined as all the entity which is written within the square brackets.
Yes.
In the square. For example, if we take again the example of, okay, let's take different example. For example, cobalt. So the H2O here, which is donating 2 electrons to the cobalt, it is acting as ligand. And all the entity which is written in this square bracket, there is cobalt H2O whole cell. It is called as coordination sphere. So these are some important terms which we should know. And now let's move to the next topic, which is the nomenclature of coordination complex.
Yes.
So shall I go?
Yes. Yes. Good. Carry on.
Okay. So nomenclature of coordination complexes. So why we need nomenclature, or who gives us this nomenclature? First thing comes in our mind. So the first answer is that IUPAC, International Union for Pure and Applied Chemistry. This is an institute which gives us the nomenclature. And why we need this nomenclature is that, for example, let's say I am staying here in Rajasthan and I am calling a compound by some name. Let's say K for FeC. I call this compound as tetrapotassium ferrocyanide. And somewhere in other state, the person can call this compound by any other name. So ultimately, this compound will lose its identity, because by different name, we are referring the same compounds. So this for retaining the identity of the compounds, and also following a particular convention that all the compounds are identified as such when they are named. So this IUPAC gave us some rules. So the rules are, first one is name of ligand. Second one is we should name the metal ion. Third thing is indicate the charge. And the fourth thing is balance the coordination sphere. So what are these naming rules? So let's look for the name of the ligand. For the name of the ligand, we should have we should know whether the ligand is positive, means ligand is negatively charged or it's a neutral. For example, if the ligand comes as Cl minus, Br minus, we name the ligand as chloro, but due to the negative charge, we name as chloride. For example, here also the name of the ligand is bromo, but due to the negative charge, we name it as bromide. And when the neutral ligand comes, we name them as such. For example, water is called aqueous. Ammonia, or it's called amine. So like this, there is a list given in the books. From there, you can look the different names of the ligand, which you have to remember. Or these are the simple. Just we can write the names as by following the convention of the negative or the neutral. Then the naming of the metal ion. Naming of the metal ion is pretty simple. Like if cobalt H2O whole 6 complex is there, the name of the metal ion is cobalt. And then indicating the charge. Now we need to calculate the charge which is present on the metal ion. Like here, this H2O is a neutral ligand, so the charge present is 3. So we can indicate the charge 3. Then balancing the coordination sphere. So if there are charge on the coordination sphere, then there must be some species like which is neutralizing Cl3. So we have to balance the charge sphere by writing that species, that is fluorine. So if I name this full compound, then I will name as hexa aqua cobalt 3 fluoride. So this is the full name. First, we indicate the ligand, and also one thing was important that we have to number the ligand also. How many ligands are present? This was the point I forgot. So we need to number the ligand also. So it's called as hexa aqua cobalt 3 chloride. Let's take another example. A for efficiency. Let's take. So here, since the potassium is appearing at first, which is having the neutralizing, so let's write first the name hexa cyano. Since the ligand is negative charge, now this whole coordination sphere is negative charge. I told you that for negative charge, we will write their ionic forms. So we can write ferrate 3. And the potassium is stabilizing the negative. Ferrate 2, the ion is in balancing. So we will write potassium, right, to indicate that the charge sphere is balanced. So like this, we can name the different coordination.
Yes, good.
So next topic is isomerism in coordination compounds. So if we look at the isomerism, there are two different types of isomerism. First one is structural isomerism. Second one is stereoisomerism. Now in that structural isomerism, we are in different type of isomerism, which is ionization isomerism. Then we have hydrate isomerism. Then we have linkage isomerism. Then we have coordination isomerism. And in stereoisomerism, we are having two types of which are geometrical and optical isomerism. Now, what are these different types of isomerism? Let's look at one by one. So, if we look at first isomerism, first one is ionization isomerism. So, let's take an example of this and understand this. If we are having a compound, okay, FeH2, FeCl3, H2O, whole thrice, SO2. If we have a coordination compound like this, in which there are two different type of ions are present, like Cl minus ion and SO4 2 minus ion. So if we ionize this, what we will get is the coordination sphere and plus SO4 2 minus ion. But if these ions interchange their position, like Fe SO4 whole twice Cl, H2O whole twice, and Cl2. This is the, and if we ionize this, what we will get? Coordination sphere and Cl1. So in this case, we are getting two different type of ions for ionization. So this type of isomerism is called as ionization isomerism. Now the next isomerism is hydrate isomerism. So what is mean by hydrate isomerism? So the hydrate isomerism is usually seen by the molecules which are having a molecule of water or molecule of hydration. So let's take an example. For example, if we have FeCl3, H2O whole thrice dot 6H2. This is a coordination compound with the hydration molecules or water of hydration. And if one of the Cl minus removes from the coordination sphere, and we get FeCl2 H2O whole 4 dot 5H2. So here the molecule of hydration has changed from 6 to the 5. Again it can change, like FeCl H2O whole 5 dot 4H2. Again it can change, like Fe H2O whole 6 dot thrice H2. So the change in the molecule of hydration or the moles of hydrate, so this is known as hydrate isomerism. Now the third one is the linkage isomerism. So the linkage isomerism is shown by a special type of ligands. What are these special type of ligands? These are ambidentate ligands. What are ambidentate ligands? So ligands which have two donation sites. But can donate from one donor site at a time. So what do you mean by that? Let's take an example of SCN minus. HCl minus is an ambident ligand. For example, if it forms a complex like this, where it donates its 2 electrons from the nitrogen side, and it can also form NCS, where it donates its 2 electrons from the sulfur. So it has 2 donor sides, but it is behaving as a single donor at a time because it cannot donate from both sides. So these type of ligands are called as ambident ligands. Like you can take case of NO2 minus. So in the NO2 minus, if it donates from the nitrogen side, then it is one position, and then it donates ONO nitrito, then it is another position, like this. Or we can take case of Cl minus, when it donates from nitrogen first, and NC minus, where it donates from the carbon. So these are the different cases where the ligand can show ambident. So what is meant by this linkage isomerism is, in a coordination sphere, when for example, this is the coordination compound where the cobalt is in +2 state and there is an ambident ligand which is NCS. Now it is donating right now from the sulfur side, but it can donate from the nitrogen side also. So if it changes its behavior, rest all the things will remain same, just the ligand will shift its position. So this type of isomerism is called as linkage isomerism. Now the last one is coordinate isomerism. Coordination isomerisms are shown by the spheres which have 2 types of coordination sphere, or which are connected as ions and cations. So what is mean by that? So if a coordination compound is formed like this, cobalt H2O whole 6 3 plus and FeCl6 3 minus, then it can interchange its ligands with one another. For example, it can form a compound like this. So this is the case when the ligands are interchanged between the different coordination sphere, and these are type of isomerism are known as coordination isomerism. So let's move to the other case of isomerism, which are stereoisomerism. So in case of stereoisomerism, we observe two different type of isomerism. First one is geometrical. So in geometrical, we are having case that there is a formation of cis and trans complex. And in case of optical, we are having compounds which are optically active. So what is mean by that, and what are these compounds? So let's look for them. So if we look for the geometrical isomerism, so for considering the optical properties or stereoisomerism, we need the three-dimension structures. So we need the geometry of the complex. So first I will tell that geometrical isomerism in octahedral complex, where octahedral is the geometry of the complex. So for example, if I am having a complex like Ma6, where A is the ligand and 6 ligands are attached to the metal center M. So in case of coordination sphere, it will look like octahedral is where 6 ligands are attached to the metal center. So since all the ligands are equal, so they can't interchange their position in the space. Even if they interchange, all the compounds that will be generated will be almost same. So in this case, there will be no isomerism. But if I take different ligands like A4, B2, Then in this, if I draw a straight line. Now in this case, you can see that B and B both are trans to each other. So this is a one case which we will call as trans isomerism. And if we draw the other form of this molecule, in which MA, B and B are close to each other, we call this as cis form. So these are the cis and trans isomerism which are shown in the octagonal. There can be different cases also which can show. So in those cases, let's see. For example, instead of octahedral complexes, if we take square cradle complex. So in this complex also, like it is having a square cradle matrix. So if we take a case of Ma2B2, this is cis isomer and this is trans isomer. And one important thing that in the other geometry, which is tetrahedral geometry, there are no geometrical isomers because it does not have a cis trans geometry, so there can't be any isomerism existence in the tetrahedral complex. So we don't study it. Now the next isomerism is optical isomerism. So in case of optical isomerism, we are having that we need the compound to be optically active. What is meant by optical activity, or what is meant by that the compound needs to be optically active is that, for example, let's take a compound. If I place a mirror on this side and draw its mirror image, I have got the same mirror image. So I can superimpose this mirror image on that. So this compound is not optically active compound. But for example, if I take which are connected like this, so in the mirror image, what we will get is this compound. Now, if I take this image and superimpose on this image, then it will be a non-superimposable mirror image. So this compound will behave as optically active compound. And the isomerism that is shown by this compound is called as an optical isomerism. Now, the next topic is the theories of the coordination complex. What are the different theories that have been given in the coordination complex?
Yes, yes. Yes, yes.
Yes, sir.
Yes, now finish.
Okay, sir.
40 minutes. Yes. Your explanation is very good. Yeah, please sit down. Yes, your explanation is very well. You explain detailed explanation. आपने बहुत अच्छा एक्सप्लेन किया है. दो टॉपिक आपने बहुत अच्छे एक्सप्लेन किए हैं. एक तो रिएक्शन मैकेनिज्म और कोऑर्डिनेशन है ना. नेक्स्ट डे हम केमिकल काइनेटिक डिस्कस करेंगे. बहुत अच्छा है. आपने 100 में 65 मार्क्स.
सर एक छोटा सा पॉइंट है क्योंकि सर जो हम पढ़ा रहे हैं तो मैंने अभी 12th का काफी पोर्शन कवर किया है. हमें वहाँ कॉलेज लेक्चर के इंटरव्यू के लिए जा रहे हैं, तो मतलब क्या हम बेसिक्स पे ज्यादा फोकस करें या मतलब अपने टीचिंग मेथड फोकस करें या फिर कंटेंट पे? जैसे कंटेंट जो